One thing to remember with magnetic field lines point away from the north towards the south. They're a dipole. That means you need both ends of the magnet for this to work. What you'll see is kind of forming closed loops. Even if they show them coming off and they don't show where they go to, those have to form closed loops because you have both attraction and repulsion. So the key to kind of remember for this section is the field lines point away from the north towards the south. And the field lines are, if you put kind of a compass needle, what direction the compass needle would point at that location. So if I move the compass needle over here, the compass needle would be pointing away. If I put it here, it would be pointing to the right. And if I put it here, it would be pointing right at the south. So inside the core of the Earth, you've got a liquid outer core and a solid inner core that actually rotates and forms a magnetic field to go all around the Earth. We use compass needles to kind of show the direction. One of the things that's a little confusing is because the compass needles are pointing to the magnetic north, what it is inside the Earth, it's as if it has a tiny bar magnet, or I should say a large bar magnet, that's got a south end and a north end. And at the geographical north, so this is the kind of equator and this is the North Pole up here, it's like it's the south end of the magnet, right? This is changing over time. It has flipped a number of times in Earth's history, and it's changing as we speak here. And we might find that in the future here, the north and the south are going to flip. So our compass needles are going to have to alter for that. Change it. Okay, so we've got 3 hand rules to kind of review. What's important is to kind of know when you're using each one. Okay, so the first one is when we just have this hooked up to a battery, and we have the electron current running through it. If we're running electron current, we're using our left hand. If we're using conventional current, we're using our right hand. Anything that's negative, electrons, anything with a -2 charge, -3, we're using our left hand for all of this unit. Anything that's either conventional current or positive charges, we're using our right hand. So if I say the electrons are traveling from the bottom of the wire up to the top, we're pointing our thumb in the direction the electron current's going, and we're wrapping our fingers around in the direction of the magnetic field. So we're looping this way. You'll see symbols to show coming out of the page as dots, and you'll see symbols that show going into the page as X's. So if I were to hold this one up, it doesn't matter how I rotate my hand, but they're coming out of the page on this side, they're going into the page on this side. And the second hand rule, if you pass me that solenoid, is anytime we get a coil of wire wrapped around kind of a cylinder here, okay? And what will happen on this is if we talk about electrons, electrons will flow from the negative end, I'll use a red, to the positive. Okay, so this is our electron flow. If it says conventional current, we're going to use our right hand, but because this is electron, we're going to use our left hand. What we're going to do is we're going to curl our fingers in the same direction for this one as the electron current is flowing. So if we think of this as my cylinder, in front my electrons are flowing down. So my thumb is going to point the direction of the north, because this is going to become a temporary magnet. As long as it's hooked up to a battery, it's going to become a temporary magnet. So when I hold it and I look at it in my hand, or if you've got a pen, you can hold it and look at it. Okay, it's curling in front. So this becomes the north end of the battery, or the magnet, this becomes the south end. Okay? The main third hand rule is now a particle entering a magnetic field. So once again, we're still using left and right. If it's an electron, we're using our left. If it's a proton, positron, alpha particle, we're using our right. The magnetic field here is going into the page. So for this one, okay, we're using our left hand. Our thumb is pointing the direction the electron is going, so its initial path. Your fingers are pointing the direction the magnetic field is, and your palm is going to point in the direction the force is going to be applied to this. So initially, when this electron comes and enters into the field, the force is going to push this down. So the force will be pushing this down. What's going to end up happening is, because the force is always perpendicular, this is going to start to curl. Okay? These are often combined with questions that talk about centripetal motion, centripetal force, and ask you to find like the charge, the velocity, the magnetic field. Once you figure out kind of the hand rules, the direction it's going, the next step is going to be just to figure out this equation and simplify for it. One thing to keep in mind, there's V's on each side. You can simplify and cut out one of the V's and then rearrange. A really common one to rearrange for is charge to mass ratio. So Q over M is charge to mass. That comes up quite a bit. Okay. There is another hand rule I'll get to in a second, but just before that, there's a couple other formulas that we're going to bump into. So we already learned this one. Magnetic force is equal to QVB. Okay, and that pops up over here. This is just the charge times the velocity times the magnetic field. So this is anytime we get a particle in a field. So if you have a question, just a particle in a field. This is if we have a current carrying wire in a field. Okay, so the current's going through the wire, it's in the field. We're trying to figure out the magnetic force applied to that. One thing to keep in mind with these questions, the only length we care about is in the magnetic field. Okay, so we don't actually care about anything outside. So the wire can be 20 centimeters long. The only point we care about is what's in the magnetic field. This is associated a lot with questions where you get a levitating wire. Okay, so you get a wire that's got enough current going through it, the magnetic field is going up, the force of gravity is pulling it down. So if it's suspended in the air, you've got the magnetic force pulling it up, you've got the force of gravity going down, okay? And we can make those two equivalent to each other, and we can solve for the current, the magnetic field, whatever we need to. Okay, so the last section is just on Lenz's law. So as a bit of a reminder, Lenz's law is whenever we get either a moving conductor in a magnetic field, or we get a moving magnet going through a conductor. So you won't often see a battery. There usually shouldn't be a battery or a power source going through. But what's happening is as the magnet drops, it creates an electric current in the copper tube. Well, we know if we get a moving electric current, that creates a magnetic field. What's going to happen with Lenz's law, the thing to remember is the magnetic field always opposes the motion. Okay? So if I look at this at the very top and I drop this, or I drop one that's got a north and a south, okay, and the north is here, what will happen is this will become a temporary magnet as it drops. Okay? That one's not as strong, so we don't get quite the same effect. As this drops, okay, or as it moves towards it, it's going to oppose the motion on this. So you want to think if you're holding the magnet, you're kind of moving this down. Okay, if this becomes a temporary magnet, what's as difficult as possible at the top? If this was a north or if this was a south. Okay, and for this one, yeah, it's going to be a north. That way it will repel as it goes through. Okay, that means the other end will be a south. Now, as it travels through, these will actually flip. They'll get weaker and weaker until it kind of flips over. But we're looking at just this point in time, just at the very start. Now think, say you're grabbing the magnet and you're pulling it up. What's as difficult as possible? Well, if this is a south and this is a north, that's going to be much more difficult to pull that apart than if it was helping you repel. So the thing you have to look at is the magnet and the direction of motion for Lenz's law. This leads us to our kind of modified third hand rule as well. Okay, so it's the same kind of as the third, where our hand is still pointing in this kind of direction, or in this orientation. What you get is a moving conductor through a magnetic field. The key for these questions is no batteries, okay, no power sources. So you've got just a wire moving through a magnetic field, very similar to the third hand rule, right? That's why it's just modified. The only thing different, instead of your thumb pointing the direction the particle's going, your thumb is pointing the direction the conductor is moving. So if the conductor is moving this way, the magnetic field's into the page. What it's actually doing is pushing the electrons down. So the electrons would all be moving down through the wire. Okay? So if I said to you which end would be more negative by the end, these would have all these extra electrons up here. This end would be more positive at the top. Okay? So the modified third hand rule is Lenz's law. The best thing I can say is look at each question and identify which situation is this. Is this first, second, third? Lenz's law, currents in a wire in a magnetic field. What is the situation it's going through? Because that'll help you limit your choices through it. Okay. Okay, one of the common questions you'll see in this unit is the cathode ray tube. This usually has two parts to it. Okay, one part where you get a subatomic particle speeding up, okay, through parallel plates. So this is really the electric field unit that we did before. And usually you'll start from rest, but this can be anything. This can be a positron, it can be a proton, it can be an electron, it can be an alpha particle, anything we want to accelerate that's a subatomic particle. So if we have to figure out how fast it's accelerating, that's our potential energy at this side is equal to our kinetic energy. Or if it had some speed already coming in and it was just speeding up, we could figure out how much kinetic energy it has by the end. Kind of we're looking for the speed by the end. So just as a reminder, we've got the voltage, the big V, times the charge, equal to 1/2 mv squared, and we can use that to find the speed at the end here. Okay? So this accelerates through, it has a speed, it's now going at a constant kind of speed as it enters into part 2. Now part 2 can be a number of different things. It can be either just a magnetic field, just an electric field, or like we see here, it's got a combination of electric and magnetic field. That's usually the most common. Okay? So in this one, you've got parallel plates with the positive plate at the top, the negative plate at the bottom. So the electric field of this, if this is a proton, or sorry, a positron, the electric field is going to pull this down, right? If I said what direction are the field lines, in this case they're all pointing down, but I've got an electric field that's going to point down. Okay. I also have a magnetic field into the page. Because it's a moving positron, okay, we're going to get magnetic force as well. So yeah, we use our third hand rule for this. It's positron, so we use our right hand, okay. Your thumb is pointing in the direction of the motion here. The magnetic field is into the page. So as it goes through, you're going to get a magnetic force up. Now, if this thing ends up going straight through, okay, without curving like I drew in the picture there, we've got the electric force pointed down, the magnetic force pointing up. And we want those two, if it goes straight through, to be the exact same size. Okay? That way, if we have any questions on, okay, what's the charge on the particle, what's the electric field, we can go back to our last unit and go, well, Fm is equal to Fe in this case. If there's an acceleration, they're not equal, but in this case, we do have them equal. It's a charged particle, so we've got QVB equal to our electric field times our charge. Okay, so you'll see this is another kind of common example for written response questions for this section. Okay, so when you see this, don't start doing immediately the third hand rule. There's kind of two different ways we can do a question like this. So if this is going, sorry, I was saying into the page, it's coming out of the page, right? For the dot here. So it's coming out of the page on a wire. So this is the first hand rule, right? So it's coming out of the page, electron current, the flow, or the magnetic field lines are drawn like this. Okay. So kind of the easy way to figure this out is if these are repelling each other, okay, it would be as if the two magnetic field directions are the exact same, because the same is going to repel. North is going to repel north, south is going to repel south. So for this to be the same then, it would go this way, around. I'm still using my first hand rule. I'm trying to figure out, okay, is this into the page or out of the page? Well, which way do I have to curl my left hand for that to happen? Like this, so my thumb is pointing into the page. Okay. The other way to kind of do this is, if you think about, you've got this one done already, okay, and you're thinking, okay, at this location, okay, if I brought an electron, if I brought another wire over, what way are the electrons going to have to move? Or which way is the magnetic force and which way is my hand going to have to orientate? So the magnetic force goes this way. The magnetic field is going up. So the magnetic force is going this way. So this is a bit of the third hand rule. Okay, the magnetic field is pointing up. The only way for this to work is for my thumb to point into the page, right? If I went like this, okay, The magnetic force over here would actually draw the wire closer to it, but because the magnetic force is pushing this away, this is actually kind of a bit of the third hand rule. So there's two different ways to do it, either the same, so they're gonna repel, or if they were opposite, they would attract there. Okay, but this is one of the questions on the retest as well. So we've got second hand rule coming up here. What we're saying in this one is inside the solenoid, I put a compass needle. In what direction is the compass needle gonna go? So first thing we gotta use is our second hand rule to figure out, okay, the electrons, yeah, flow from negative to positive.
Down.
So it's down all in front.
And this was north.
Yeah. So this is the north end, this is the south end. That means when we draw the field lines come from the north, I'll use black maybe here. Come from the north and point towards the south. So they're pointing away from the north towards the south. The instinct is, okay, well, this is always gonna point to the south, but follow the field lines. That's kind of the key for the ones where it's inside. So if I continue this all the way through, the field lines form a loop.
Oh.
So inside, it ends up actually pointing to the north, but it follows that loop throughout.
Okay.
Okay?
It's tricky.
That is a tricky one. So that's on the retest.